we now have a complete description of the hydrogen atom wave functions. Our starting point was the time-independent Schrödinger equation, expressed in 3 dimensions with a Laplacian of the wave function as part of the kinetic energy term. Applying our usual separation of variables to this function, meaning psi of r, theta, and phi, using spherical coordinates since our potential in the case of the hydrogen atom is a function only of radius, we're separating a radial equation from an angular equation. Our angular equation, the result of separation of variables, is this, and it's complicated, but the solutions we got after repeating the separation of variables, separating theta and phi, was these spherical harmonics, YLM of theta and phi. This angular equation is something that you get many times in treatments of partial differential equations, like the Schrödinger equation, in 3 dimensions in spherical coordinates. These are the sorts of things that you get when you solve for the wave equation on the surface of a sphere, for instance. These spherical harmonics are essentially vibrations of a spherical membrane. For the radial equation, what we got after the separation of variables for capital R, that function, was this. And this equation was slightly more complicated. We didn't just get simple sorts of YLMs that we could write down. YLMs being given in terms of a set of orthogonal polynomials and complex exponentials in phi. We end up with the same sort of solution for our radial equation, though. The process is slightly more complicated. Our capital R of R function, we had to make some changes of variables, but what we got in the end was R sub nl as a function of R. As a change of variables, we ended up with a 1 over R, simplifying things to write things with this 1 over R factored out. And then factoring out asymptotic forms, and before we did a power series solution, we get R over an raised to the L plus 1 power times e to the minus R over na. Those were our asymptotic forms, and then we ended up with some polynomial of R over na. And these polynomials ended up being associated Laguerre polynomials after we did a power series solution here. So we have a complete mathematical description. This A, incidentally, is the Bohr radius. It's a length, about half an angstrom, if you plug in the actual values of the constants. So we have a great deal of math here. Let's see what this math actually looks like. Messy. The final normalized hydrogen atom wave function has 3 quantum numbers, n, l, and m. The energy associated with this is given only by the n quantum number. The L and the M come from our spherical harmonic portion, and we end up with some complicated normalization constants. Normalization constant out front, then we have our asymptotic forms for our radial function. The actual meat of the radial function is this associated Laguerre polynomial with various orders, and the angular part is given just by our spherical harmonics. So it's hard to looking at this to visualize what this actually looks like. So let's consider some sample cases. First of all, n, l, and m is 1, 0, 0. This is the lowest energy, the ground state, and it looks rather boring. What visualizations like this actually show are surfaces enclosing regions where the particle is likely to be found. So really, this doesn't tell you with certainty what the wave function looks like, because the wave function is, of course, a complex valued function of all 3 dimensions. It's not simply the expression for a surface. Our radial wave function, for instance, if we plot it here, R of R, is going to end up just looking like a decaying exponential. If we're looking for where the particle is most likely to be found, we also need to consider the spherical harmonic component, but in the case of the spherical harmonics, L is 0 and M is 0, and the spherical harmonics are simply constant. So our wave function more or less looks like this function of radius only, which tells us that the particle is likely to be found near the origin. So if you have some threshold within which you're likely to, or you consider the particle likely to be found, say probabilities higher than this, you end up with radii less than some critical radius. And that's what this sphere is showing you. It's a sphere with some radius given by whatever threshold you happen to use. So if this was boring, Let's find out what happens if we look at N200, or NLM is 200. Well, that one's kind of boring as well. It's not quite as boring, though. It's just difficult to see in this. If we sliced this in half, there would actually be a region where the particle is unlikely to be found inside this sphere. If we look at our radial function, again, our spherical harmonics being trivial, the radial function is the only one that matters. It decreases, drops below 0, and then comes back. So if we have some threshold above which we're interested in, or we consider the particle likely to be found, say here or here, we actually have two regions where the probability of finding the threshold is, or finding the particle is above threshold, inside and outside. So if I slice this in half, if I draw a coordinate system, and I'm just going to show the bottom half of the sphere now, I would have some internal region where the particle is likely to be found, and some external region within which the particle is likely to be found. Sort of two concentric spherical regions where the particle is likely to be found. These are not disks, of course, these are spheres, so I really ought to shade these in accordingly, but that would just make the figure even harder to read. These cases where L and M are both equal to 0 have spherical symmetry, since the spherical harmonics, the part that gives you dependence on theta and phi, is trivial, it's constant. So for the case of of L and M both equal to 0, you just end up with concentric spherical sorts of shells where the particle is likely to be found. The number of regions where the particle is unlikely to be found, here, where the wave function crosses 0, is essentially given by n minus 1. In this case, we have one place where the particle is unlikely to be found, this region in between the two concentric spherical shells. If we go up to cases where L and M are not equal to 0, you get something like this. This is L equals 1 and M equals 0. Now we have two distinct regions here, and I'll draw this in cross-section. I'll make figures like this repeatedly in, say, the XZ plane. And there's a region where the particle is unlikely to be found, on the XY plane, for instance. Which leaves us with two regions, one above the plane and one below the plane, where the particle is likely to be found. The fact that the colors are different here is telling you something about the relative phase of the wave function. The fact that these are sort of opposite colors, blue and yellow, are opposite in a circular sort of RGB, going from red to green to blue and back to red. Blue and yellow are on opposite sides of the circle, so these have opposite phases of the wave function. When the wave function is plus 1 here, it will be minus 1 here. When the wave function is plus I here, it will be minus I down here in this region. All of these are, of course, evolving in time, so if I made movies of these, the colors would be fluctuating, but they would always be opposite colors on opposite sides of the XY plane here. If you look at the case where M now is plus or minus 1, we get a slightly different shape. This may look a little unfamiliar if you're used to looking at pictures as drawn by chemists. Chemists don't like to deal with complex numbers, which is understandable. They're dealing with real things. Why would they need complex numbers? But in physics, we're dealing with wave functions which are expressed in terms of complex spherical harmonics. What that means, here, our YLMs have something that looks like e to the I plus or minus 1 times phi. M is 1. So this is plus or minus Im phi. So I plus or minus 1 phi. So what we're looking at is phase of the wave function fluctuating as we move around in the phi direction. And the fact that the colors are different here indicates that the sign of the evolution of phi is different. For instance, here we go Roy G. Biv, red, orange, yellow, green, blue, violet, around clockwise, whereas here we go red, orange, green, blue, violet, around counterclockwise. So the direction of our evolution of phi here is opposite. It's hard to draw pictures in that cross-sectional plane sense that I drew earlier, if we're talking XZ plane for both of these. But they don't actually look all that different. Where is the particle not likely to be found? Along the z-axis. And for that, I'll draw a dotted line along the z-axis. If what you're used to looking at are the orbitals from chemistry, you're probably used to seeing pictures that look something like this. You have a blob over here, you have another blob over here. Or you have a blob over here and another blob over here, sort of along the x-axis or along the y-axis. You get these by combining superpositions of these two complex spherical harmonics. Essentially, what you do to construct the real spherical harmonics is to superpose the complex spherical harmonics. For instance, if I take this, which is e to the minus I phi, and this, which is e to the plus I phi, and I add them together, this is going to give me cosine phi plus I sine phi. This is going to give me cosine phi minus I sine phi, after I abuse the even and odd properties of cosine and sine. If I add these two together, for instance, I'll get cosine of phi plus I sine plus cosine minus I sine, and the I sine parts will cancel out, leaving me just with the cosine part. The cosine part, then, is going to be non-zero only along the x-axis, where phi is 0. If I combine them instead with the minus sign, I'll get the cosine parts to cancel out, and I'll end up with minus 2I sine phi. If you ignore the complex part by multiplying everything by I, for instance, you'll end up with just the sine of the angle, and you'll get something that's only non-zero along the y-axis. So you would get the same sort of two blobs that we saw when we looked at the case where m equals 0. So if you're seeing pictures with blobs off-axis like this, in the case where m is non-zero, you're looking at a chemist's interpretation of the spherical harmonics. We can keep going. I'm going to skip the case where NLM is 3, 0, 0, since you know what that's going to look like. It's going to have 3 concentric regions where this particle is likely to be found, and go straight to the case where L equals 1. This is m equals minus 1, m equals 0, and m equals 1. So once again, Roy G. Biv clockwise versus Roy G. Biv counterclockwise. For the case m equals 0, we don't have any complex exponential part, so we just have the plus or minus 1 sort of phase differences. We also don't have any azimuthal dependence, and our radial structure ends up having one radial node. So we're unlikely to find the particle at the origin. We're also unlikely to find the particle in this sort of spherical region here. And the angular regions where we're unlikely to find the particle depends on what spherical harmonic we're looking at. So in this case, we're unlikely to find the particle along the z-axis, and we're unlikely to find the particle at a particular radius. Same sort of picture for this one, except we're looking at azimuthal dependence in a different direction. Unlikely to be found on the z-axis, unlikely to be found at a particular radius. The picture for m equals 0 is that the particle is unlikely to be found on the xy plane and at a particular radius. So what I'm drawing down here is the structure of the nodes, the regions where the particle is unlikely to be found, since those are really the boundaries between the blobs in pictures like this. We can keep going higher still. This is if L equals 2 in the case of n equals 3. So the structures we get are slightly more complicated still. The case where m is as large as it can be here, this is m equals minus 2, m equals minus 1, m is 0, m is 1, and m is 2, always look the same. We have the particle unlikely to be found along the z-axis, and we have this sort of donut shape going around. If I draw my node pictures for this, my m is as big as it's going to get case is always going to look the same. It's unlikely to be found along the z-axis. If I draw my node pictures for this case, the particle is unlikely to be found along the z-axis and unlikely to be found on the xy plane. So we have sort of two separate donut shapes. For the case m equals 0, the particle is unlikely to be found at two values of theta. So I'm going to draw two lines like this, and you'll have to keep in mind that these are representing cones rotated around in the xy plane. Essentially there's a cone here and a cone down here where the particle is unlikely to be found. I'm going to erase that since it wasn't terribly instructive, but you get the idea. There are two angular nodes, two places in theta space where the particle is unlikely to be found. The same pictures, of course, apply over here and over here as they did here. Particle, in this case, unlikely to be found in the xy plane and unlikely to be found along the z-axis. This particle being unlikely to be found on the xy plane really refers to a node in theta where the the spherical harmonic evaluated at theta equals pi over 2, rotating 90 degrees down from the z-axis, is 0. So that defines the xy plane. Similarly, of course, over here, particle is unlikely to be found at theta equals 0 or theta equals pi along the z-axis. So these are the sorts of structures that we get from spherical harmonics. If you make superpositions of these, the way the chemists like to, you need to keep in mind now that, notice we have 2 points along the m equals minus 2 and m equals plus 2 where the color is red. That's because we're looking here at something like e to the 2i phi minus 2i phi in this case, and e to the 2i phi in this case. And when I superpose those, I'll end up with sine 2 theta or cosine of 2 theta. So I'll end up with pairs of blobs. If I draw that out in 3 dimensions, you'd end up with blob, 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 versus, in this case, the same sort of thing, but rotated 90 degrees. So sort of blobs on axis versus blobs off axis. It's very hard to tell given these tiny sketches. So I suggest you go and look at pictures from the chemist's perspective if you're curious. You probably have a chemistry textbook or can find pictures online quite easily. As before, in physics, we're not afraid of complex numbers, and we end up with these sort of circular shapes for the non-zero values of m in our spherical harmonics. From the chemistry perspective, I'm going to go back through these slides again. These spherical orbitals are called s orbitals. The L equals 1 orbitals here, where we have these blobs, or in our case, donuts, the blobs are the chemist's approach, are called p orbitals. And the case where L equals 2, we have the slightly more complicated structures. These are called d orbitals. The origin of those names comes from a really antique spectroscopic convention, where the spectral lines that are emitted by an element are named according to their structure. Sharp for s orbitals, principal for p orbitals, diffuse for d orbitals. We now know that that doesn't really have a lot of comparison or relevance to the actual structure of the orbitals, but the names have stuck. To check your understanding of what the hydrogen atom orbitals look like, here are a couple of things that you can try using the simulations at Falstad.com. He has a hydrogen atom orbital visualization tool, and you can use it to make complex combinations. So there are some specific things that you need to do in order to answer these questions on those simulations, but I encourage you to play with this simulation and try and get a feel for what the orbitals look like, both from the chemist's perspective. Those are real real hydrogen atom orbitals, as opposed to the physicist's approach, which is the complex approach. So the specific sub-tool of this visualization that I'm suggesting you use here to answer these questions is complex combinations of orbitals with n equals 1 through 4. But you can look at the real orbitals as well and make combinations of the real orbitals as well. So that's about all I need you to understand about the appearance of hydrogen atom wave functions. These things are, of course, very important from the perspective of chemistry, but from the perspective of physics, it's really just these complex wave functions, which have a variety of quantum numbers and a variety of geometrical representations, a variety of geometrical structures.